Okay, in the last video we took a look at an introduction for nodal analysis, which was kind of our first, introduction into basically systematic processes based off the property of linearity. And if you remember from the nodal analysis video, it was an application of KCL, Kirchhoff's current law, in order to find unknown node voltages. And one thing I really like about basically nodal analysis is that all the currents going through each element were directly related to the currents going through that specific element per se. With loop analysis, we're actually going to be concerning ourselves with the utilization of Kirchhoff's voltage law in order to find unknown loop currents. And we're going to talk about what loop currents really are and how that a current going through an element may actually be made up of multiple loop currents. And it's more of a, to me, at times an abstract process for students, but it's also the easier of the two methods as far as my experience with students catching this stuff really quickly. Most of the time, once I see students go through this lecture, they could easily just take the test and be done with it. It's very simple, and I think part of it is because fractions scare people just in the same way they scare me. I don't like them. I like to go ahead and convert those into decimal form. But loop analysis, or you'll hear it called mesh analysis, is an application, systematic application once again, of Kirchhoff's voltage law to find unknown loop currents. And just like nodal analysis, once we go ahead and find the loop currents, we can find every every voltage or current, any information that we need to know about that system right away. The systematic process works beautifully, and also we can apply this with AC analysis way down in the future. So very similarly with nodal analysis, with loop analysis, we have almost the same steps, but in a little bit different. First, we draw our assumption of the loop current flow. And just like nodal analysis, it doesn't matter what that assumed current actually is as far as its direction, because essentially the math will do the work for us, which is once again a very cool thing. And number two, we label those loop currents as I1, I2, etc. And we apply KVL, write out a KVL equation, and then we expand each KVL equation by Ohm's law once again and combine the like variables. And by the time we do that, we have to solve the system of equations with linear algebra. So very similar to the nodal analysis method, except this time we're utilizing KVL and we're utilizing loop currents in order to find basically the values of those currents in each loop. So let's take a look right here about what we mean by loop current. Now, at the very beginning of the class, I discussed essentially how many loops we would actually see within a circuit. And if you remember, I normally did not count the outer loop that's flowing from the source through R1, R3, R4, and then back. Is the outer loop technically a loop in the circuit? Yes. But I said just go ahead and stay with essentially the most identifiable closed loops. And if we look at this, we have two. We have basically one loop here and a second loop. And the reason why I said at the very beginning of the class to kind of ignore this outer loop here is because once we get to loop analysis, if we utilize a third loop, we basically get a third system equation that actually doesn't really do much for us as far as finding these values of the currents. So let's talk about what loop currents really are. And so literally we draw a loop current within each single closed loop, and I denote this one as I1 and this one as I2. And allow those to flow clockwise in this case. And most of the time I like to draw them clockwise, but we're going to talk about how, and we're going to demonstrate also how those currents can flow whatever direction that you want. And once again, just like nodal analysis, as long as you are consistent up front about how you draw those currents and then apply KVL, or with nodal analysis, how you apply KCL, the math will do the work for you. And if you get a negative symbol, then you realize your current was drawn backwards, essentially. So the one thing about the loop current is that anytime we analyze or write out a KVL equation reference to that loop current, we always assume that every element, every resistor within that loop is essentially going to follow the rules of passive sign convention. So current goes into the positive terminal, leaves the negative terminal. And this concept can kind of throw students off just a little bit. I'm going to say this again. We're going to see why in just a second. That every loop current we reference to basically passive sign convention, once again, that current will render a positive to negative orientation current going into the positive terminal of the resistor, leaving the negative terminal of the resistor. Let's see what we mean by that. Now, if we look right here, in this loop current that I've drawn clockwise, by passive sign convention, we would say that the voltage applied, potential differences applied across R1 would be positive to negative, left to right in that orientation. If we look at R2, here with that loop, reference to that loop current, we have positive to negative in that orientation. So let's take a look over here at I2. Once again, positive to negative, referenced to I2, the flow of I2. Positive to negative for R3, positive to negative for R4. But look at this. As that loop current I2 moves back around, here we actually have positive to negative for R2, where the polarity is in reference to I2 is backwards from the way it was referenced in I1. And what we're really seeing here is that the total current that's flowing through R2 actually is going to be a combination of I1 and I2. And we're going to see what happens with that as we get into the equations, the expansion of the KVL equations. So let's go ahead and take a look at loop 1 right here. Now everything in this lecture is symbolic. We'll get into more examples, things like that during class time. So with loop 1, Vs is equal to VR1 plus VR2. Sure enough, voltage across R1 plus the voltage across R2, passive sign convention, and that's equal to the voltage rise of Vs. And if we go ahead and expand that out by Ohm's law, then we would see that the voltage across R1 is in fact equal to R1 times I1. And I think we can all see that, R1 times R1. So let's say R1 times I1, may have messed up on that. Okay, so look right here though. We get down to, and that was supposed to be a 2 right there, sorry. So when we get down to R2, we actually see that the total current flowing through R2 is actually a combination of these two loop currents. Now that may sound weird to you. What is that total current that's actually going through there? Remember, this is a systematic process, and because of the property of linearity, it allows us to be able to write out these equations in terms of basically these loop currents, a combination of I1 and I2. So if we consider and reference I1, then here we would say the voltage across R2, because they are going in opposite directions, is equal to R2 times I1 minus I2. So I1 minus I2. Think of it like this. If you're walking across Chattanooga State and you have a headwind in front of you, then you're going to have to walk a little bit harder in order to get to your class. However, if you got a tailwind, it's actually going to make it easier for you to walk back across campus again. Or if you're flying from Dallas-Fort Worth to Atlanta, generally you have a tailwind, captain comes online, says, ladies and gentlemen, this is your captain, we're actually going to get in a little bit early. If you're going from Atlanta to Dallas-Fort Worth, you generally have a headwind. You're always late to Dallas-Fort Worth, and you always worry if you're going to miss your flight if you didn't plan ahead a layover. So that's basically what's happening here. We have the currents actually moving opposite of each other. Generally what happens here with two clockwise loops is that they're actually going, once they get to the inner, R2 that divides the two loops out, they're going to have an opposite effect on each other, just flow against each other. So here, that's why we say we have R2 times I1 minus I2. We always put the reference loop current, I1, that variable, with loop 1. So once we do that, we want to go ahead and write out the system equation by combining all the like variables together. And the like variables of I1 would actually have the coefficients of R1 plus R2, and then minus R1 times R2. So let's take a look at loop 2. Loop 2, there is no voltage gain over here. There is no voltage rise at all. Basically, there's no separate excitation, so for the summation of voltage rises, we have 0, and that's going to be equal to R3 times I2, so positive to negative, sure enough. Once again, we're referencing this loop as each element, the I2, that loop current is driving the polarity of positive to negative because current goes into the positive terminal of the resistor. So we also add on R4 times I4 plus R2, but in this case, because this is the reference loop, we're analyzing writing out our KVL equation for loop 2. We would say R2 times I2. We put I2 first minus the effect of I1. So we subtract off I1 in this case. And we go out, combine our like variables, and that comes out to be equal to minus R2 times I1 plus R2 plus R3 plus R4 times I2. So just note right here that when I write out the equation for loop 1, I always put I1 first. Okay? Always put I1 first. And that just keeps things nice and clean. Same thing with loop 2. I always right here would put, when we're looking at the currents impacting each other, I always go ahead and put the current that we're actually referencing for that equation. Sure enough, this is for loop 2. Okay. So this is a very, very simple, basic way that we can actually analyze these, but let's flip it up, because remember what I said, that it didn't matter how you drew those directions of the current, as long as you stay consistent. But what happens if we have currents moving, some moving clockwise, some moving counterclockwise, and let's start adding maybe a few more loops to this. I mean, this is just very, very basic. Probably looking at it also and wondering, well, Mr. Morley, why do we even want to put system equations here? We can just break down the circuit and easily find the elemental current. Well, this is a very, very basic two-loop circuit just to denote the process. So what if we can't break down the circuit? And that's where, just like nodal analysis, the systematic equations really help us and really give us a path for actually analyzing circuits that we can't readily break down with equivalent resistances and utilizing voltage division or current division. So let's see what happens when we start having a little bit more difficult circuits. All right, so here we got a 3-loop circuit. And as you're looking here, you probably can see, oh, now we actually have 2 sources in 3 different loops. So for this one, that means that we're going to have 3 system equations in order to find basically the loop currents I1, I2, and I3. And just like before, guys, when we expanded out that KVL equation, we saw that for the resistors that are kind of in between two loop currents, that the total current that's in there is actually made up of those loop current values. So in this case, let's see here. For this one, I actually said that I would allow I1 and I2 to go clockwise, and I3 is actually going counterclockwise. So we're going to see a cool effect that actually happens within our analysis method right here. The camera turn off? Nope, we're still going. Had that happen yesterday. It's kind of weird. So let's take a look, and let's just go around the closed loop of each of these. And I always kind of suggest at the beginning, to help you with the analysis technique, to go ahead and just draw the positive and negative orientations for each loop. It just kind of helps with your equation and gives you a way to check yourself. So here, for I1, positive to negative in that orientation. For R2, positive to negative. And for R3, positive to negative. So in this case, if we look at I2, well, obviously right here, I2 is going to flow against I1. And so that means that we're going to have a positive to negative orientation for that polarity for R2 in that manner for I2. And then also for R5, positive to negative, positive to negative. Let's look at loop 3 here. Positive to negative for R1, positive to negative for R5, positive to negative in that orientation for R4, and positive to negative in that orientation for R3. So now we can actually go through and start writing out equations. So let's take a look first at loop 1. So V1 is equal to R1 times, oh look at this, positive to negative are in the same orientation. They're not opposite of each other like it was in the prior example. They're the same, and what we can see here is that the two currents are actually flowing together. They're flowing together, and so because of that, here we get I1 plus I3. I1 plus I3, they combine together. And so once we actually find our values for I1 and I3 through the systematic process, the total current flowing through there, all we would have to do is just add those two values that we had once we actually solve our matrices. And if we wanted the voltage, all we have to do is multiply that by R1, and that would give us the voltage across, the true voltage across R1. Let's continue on. Let's take a look at R2. We have two opposite polarities, and we can see here that that's driven from these two currents flowing against each other. So once again, I put I1 first, subtract off I2, multiply that by R2. And then finally, with R3, add on R3 times I1. Go ahead and combine like variables for I1, I2, and I3. And so we get R1 plus R2 plus R3 times I1, and then minus R2 times I2, and then plus R1 times I3. Let's take a look at loop 2. So for loop 2, as we can see right here, that current, we're going to start off with the voltage rise, but because usually this would be a constant, we're going to move it over to the other side because in fact actually this is a voltage drop right here, right? So here we're going from positive to negative, and so we're actually going in terms of a voltage drop over here, so we actually would say negative V2 because that generally would be a constant. And then once we get to R2, now we're going to consider the two currents once again flowing against each other. So R2 times I2, remember this is loop 2, this is the current that we're referencing, the loop current that we're referencing, so we put I2 first and subtract off the effect of I1. And notice how these two are different right here. But here in loop 1 we said I1 minus I2, in this one we say I2 minus I1. Now let's take a look at R5. Both polarities for each loop are actually the same, meaning also that current is flowing together. And if they're flowing together, we just add the effects together. So R5 times I2 plus I3, and then plus R6 times I2. Okay? Go ahead, combine like variables, so we get minus R2 times I1 plus R2 plus R5 plus R6 times I2, and then plus R5 times I3. Now if we look at loop 3, here we have 0 because there's no separate excitation in there, and that current's moving counterclockwise. And so for here we're going to have R1 times I3 plus R1, note again I put I3 first, plus R5 times I3 plus I2, plus R4 times I3 plus R3 times I3. Go ahead and combine our like variables, so that's going to be R1 times I1 plus R5 times I2, plus R1 plus R5 plus R4 plus R3 times I3. Okay, so that would, if we actually had variable, well, constants for each of these resistor values as well as the voltages, we would actually be able to formulate basically a matrix that consists of 3 simultaneous equations and be able to row reduce it, put it in echelon form, and that way we would actually be able to get all values that we wanted for each current within the circuit. But once we get that, once we get the values for I1, I2, and I3, then we would actually be able to find the true current that's going through R2, that would be I1 minus I2, or the true currents for R1, which would be I1 plus I3, or our R5, which would be I3 plus I2. Brilliant. And then we could easily find the voltages of each once we know the true current. If we ever get values that are negative for I1, I2, or I3, that just means that our assumption of the current flow is actually backwards. In fact, I would probably guess that I would get a negative value for I2 because I allowed that to go opposite of the polarity of our voltage source. But the math will do the work for us, and it's knowing how to interpret that math as well. So, man, I think this is the 53rd video I've made within the past few months, and it's really, really weird, like, not being able to ask students questions in this room. Literally, I'm talking to a camera right now with a whole entire room of basically no one in here. It's kind of odd. It's like 5 o'clock on a Friday afternoon. I got no life. What can I say? All right. So let's do a third example, and we'll call it good for today. So as you guys probably guessed, I went ahead and cranked it up a notch with this one. And, well, I added a couple of things. I added a 4th loop here, and also I added a current source. Oh, man. What are we going to do with the current source if we put that within a massive loop right here? So for this one, we have basically 4 loops. We need 4 simultaneous equations in order to find these values. We're going to see something really unique happen with I4. So we'll see that. So let's go ahead, draw out our assumption of the loop currents. Doesn't matter. Doesn't matter. You could do it differently than I did. You could take all of these and make them go counterclockwise. Doesn't matter as long as you stay consistent with the KVL equation. Okay? So here, I'm going to let I1 be clockwise, I2 be clockwise, I3 be counterclockwise, and I4 be clockwise. I just said, I'll just let it be in the same direction as the current source. So here, positive to negative for I1, positive to negative for R1, for R2, positive to negative, and then for R3, positive to negative, and that orientation for passive sign convention for I1. When we look at I2 is going to flow positive to negative for the 3rd voltage source. Here, R5 is going to have a positive to negative orientation in that manner, positive to negative, positive to negative. So here for V2, it's going in the opposite direction, so positive to negative, positive to negative, positive to negative. And with I4, we're going to see that the voltage polarity is actually going to be opposite for R3 in reference to that loop, and also the same polarity in reference for I4 compared to I3 for the 4th resistor. All right, so now we can go ahead and just write out our KVL equation for each one of these, and then basically set it up so that we have 4 equations, 4 unknowns. Let's see what we get here. Well, it looks like I1 and I2 for R2 flow against each other, so we know that we're going to subtract off I2 in that manner, but here for R3, we're going to see that I1 and I4 combine together. So for loop 1, V1 is equal to R1 times I1 plus R2 times I1 minus I2. Remember, they're flowing against each other, plus R3 times I1 minus I4, once again flowing against each other. Go ahead and combine like terms here. R1 plus R2 plus R3 times I1 minus R2 times I2 plus 0 times R3 minus R3 times I4. I went ahead and put this in here because when you guys actually develop your matrices, if you don't, that should be an I right there. I am sorry. Whoops. So, because there's no third loop current actually impacting this loop up here, we have to say 0 times I3 because when we put into our matrices, if we don't include that, it's going to throw everything off. So we always have to make sure that in our simultaneous equations, we're always accounting for each variable. Let's take a look at loop 2. So for loop 2, I2 is moving positive to negative, which signifies a voltage drop. So we would say negative V3, and that's going to be equal. Let's look at R5 first. Looks like both currents are flowing together, so we're going to say R5 times I2 plus I3. Get to R2. This time, because we're referencing the second loop, R2 times I2 minus I1 plus R7 times I2. Go ahead and combine our like variables. We get minus R2 times I1 plus R5 plus R2 plus R7 times I2 plus R5 times I3 plus 0 times I4. Let's take a look at loop 3. Here, loop 3, that current's coming out of the positive terminal of our source. So we're going to have V2, and that's going to be equal to R5 times I3 plus I2. Yep, that makes sense because I3 and I2 are once again flowing together with each other. But notice once again I put I3 first here. Compared to up here at loop 2, I put I2 first. Always put the loop current for the loop that you're referencing in your KVL equation first. Plus R4 times I3 plus R4, sure enough, I3 and R4 are moving together. Plus R6 times I3, we combine our like variables. Once again, we get 0 times I1 plus R5 times I2 plus R5 plus R4 plus R6 times I3 and plus R4 times I4. So for loop 4, this is the one that's a little bit different. So the current source is actually driving that value of I4 directly. So I4 is just equal to IX, guys. That current source is driving that value directly. Bam, right there. And so there's a couple of ways that we can handle this. If we just went ahead and left that in terms of basically being I4, we could actually just go ahead and substitute that in all 3 equations. So we would have 3 equations, 3 unknowns, because basically IX is driving I4 to be that value. It's a current source, that's what it does. So we could do that, or we could just go ahead and write out a simultaneous equation here, where we would say 0 times I1 plus 0 times I2 plus 0 times I3 plus 1 times I4, and that would just be equal to IX. And once we actually go ahead and develop our matrices and perform row reduction, this would actually substitute that value in to the other 3 equations. So it's up to you if you want to go ahead and develop 4 equations out of that, or substitute in that value of I4 because of that current source. Either way, it works just fine. But it is always kind of cool to actually show that once you substitute a simultaneous equation in this manner into your matrices, this value always comes back out to be the current source, which is pretty cool to me. All right, so you guys should be working on your homework. Got some chapter 3 homework specifically for loop analysis that you guys should be taking a look at now. And we'll come back and discuss that in class. See you then.